Hey, I'm Courtney Waterman, your tutor. Lover of anime, manga, and math. And you just tuned into another session of Tutor Me Senpai. Welcome back, everyone. Today we're jumping into a 12th grade topic, using your geometric series formula. Now, if you're new to my channel, I'll be putting time codes in for this video in the description box below, so use that to skip ahead to whatever part of the video you think is most interesting. As always, if you have any questions about what we see today or even your own homework, you can always put in the comment box below or visit my Facebook page at Tutor Me Sempai and tell me all about it there. At the end of this video, I'll be linking my 12th grade playlist, in which I cover a lot more topics, so if you're interested in that, make sure you stay tuned. This video is going to have 4 parts, so leave a like, smash subscribe, and let's get started. In my previous video, we covered our geometric series, and I showed you what the formula for that series would be if you had to evaluate it. However, I didn't talk much about it, mainly because I wanted to focus a little bit more on this video, do a deeper dive into using it and all its different facets in this video. However, if you hadn't seen that previous video, no worries, you can find it right up here. But if you recall, our formula for when we're trying to evaluate our geometric series is going to be as follows. We have our a sub 1 all over 1 minus r times our 1 minus r to the nth power, where a sub 1 is going to be our first term, our r is going to be our common ratio, and our n is going to be the number of terms we have in our series. And similar to our arithmetic counterpart, this is going to be the formula that we're going to be using to evaluate our finite geometric series. However, unlike our arithmetic counterpart, this formula can actually also be used to evaluate some, not all, but some infinite geometric series. You'll see what I mean by that in a little bit later on in this video. However, when asked to evaluate your geometric series, you may be asked in a few different flavors, such as you can have the entire series written out like this, you can have some information about your series written out like this, or you can have it in sigma notation. It doesn't matter in which flavor you get, you can still use this formula to evaluate your geometric series. The main thing you need to remember is find your 3 components of this formula, and if you can do that, then you can plug them in and get your answer. Remember, you need your a sub 1, your first term, your r, your common ratio, and your n, the number of terms you have in your series. Now that we've been introduced to the basics of this geometric series formula, let's use the formula to evaluate a finite geometric series. Let's say we have this finite series here, and we want to evaluate it. Well, first thing you want to ask yourself is, how do you know it's finite and not infinite? Well, notice we have a 10 here. This is saying that we're going to be adding up this formula here that calculates each part of our series, each component of our series, each term of our series, and we're going to be plugging in this k to evaluate what that term is, and we're going to add up each and every one of them until we get to the 10th term. So we have a fixed point that we're shooting for, 10. Now, if this was, instead of 10, infinity, then it would go on forever. And that would be the infinite series there. It would be an infinite series if you had this infinity, because there is no fixed point that we're stopping at. However, we have a 10 here. This shows us that this is going to be a finite series. That means we're going to be able to just plug this in as we find our components. And if you recall, the 3 components you're going to need are going to be your a sub 1, your r, and your n. So do we know what our a sub 1, our r, and our n would be for this series? Well, n, we just talked about it, was 10. We're going to be stopping at 10. Our r looks to be 2. It's what's inside this parentheses. And our a sub 1 is going to be whatever this evaluates to when k is 1, our first term. So we can just plug this in. So we have negative 2 times 2 to the 1 minus 1. And this is going to be 2 to the 0, which we know to be 1. So our a sub 1 is just going to be a negative 2. We're going to just plug in our negative 2 here. Now that we have all 3 of the missing components that we needed, let's plug them into our formula and see what we get. So we're going to have as follows. And if you were to further simplify this, you would get the following. Continue simplifying, you're going to get the following. And lastly, we're going to have, this lets us know that we're going to evaluate this series to be negative 2046 when we're going from 1 to our last term, which is 10. And like I said in a previous part of this video, it doesn't matter how they ask the question, as long as you can find these three missing components, your a sub 1, your r, and your n, you can plug them into this formula and evaluate your series. So finite series seem simple enough. How about your infinite series? Let's move on to evaluating, when we can, our infinite series. Before we jump into evaluating our infinite geometric series, we have to first ask ourselves one very, very important question. Does our series converge or does it diverge? If we have a series that converges, then we are good. We can use our formula to evaluate that series, even if it goes into infinity. If it keeps growing, keeps adding more and more terms, we can still evaluate that series. However, if it diverges, we cannot. Unfortunately, there's nothing we can do. It just keeps growing, and there's no fixed point that we can kind of pinpoint and say that's going to be the sum of this series. Well, how do we figure out if it converges or diverges? Well, that's going to be determined by your common ratio. Let me show you what I mean by that. Let's look at our formula here. We have a sub 1 over 1 minus r times 1 minus r to the nth power. And as we're adding more and more terms to our infinite series, the only thing that's going to be changing here is this n. Our a sub 1 is pretty fixed, our r is also fixed, but n is going to be growing as the terms keep increasing. So that means that the thing that it's tied to, this r to the n, is also going to potentially keep growing. Let's say we have an r equal to 10. Well, that's going to be, let's say 10 squared. Our second term is going to be 100. Let's say we have 10 to the fifth. Our fifth term, that's going to be 100,000. Well, that just means this is getting larger, or magnitude-wise, it's getting larger and larger as the n increases. As you're going to be increasing your power, this top value is going to get bigger and bigger. Not necessarily more positive or more negative, but we're thinking absolute value just getting bigger and bigger. It's not going to converge into a single number. It's just going to keep growing. So if you pick an arbitrary n super, super large and you plug it in, let's say you had an r equal to 10, this is going to be massive. It's just going to keep getting bigger and bigger. But is this going to be true for all values of r? It's true for 10, but is there a value of r that would actually get smaller as you're increasing its power? Well, yes, we have fractions. Well, not all fractions, but certain fractions, when you're going to increase their power, they actually end up getting smaller. So let's say we have, instead of 10, let's say our r was 1 over 10. So the same thing applies. So we have 1 over 10 squared is going to give you 1 over 100. And we have 1 over 10 to the fifth is going to give you 1 over 100,000. Notice that this is getting much and much smaller. However, it's not going to just keep getting smaller and hit negative infinity, whereas the other one was just getting larger and larger and larger. This is going to get smaller and smaller, but there's going to be a cutoff that is never going to pass. What is that cutoff? Well, if you keep growing this exponent, you'll notice that it gets closer and closer and closer to 0. It's going to get infinitely close to 0. It's never going to get there, but it's going to get infinitely close to 0. This is pretty much limits. However, we'll cover limits in another video. But this is letting you know that as you're going to be growing this exponent, this number is going to get very large in the denominator, causing the whole thing to get very, 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 very close to 0. But how does that affect our formula if that happens? Well, pick a very, very large n out there. And this r to the n is going to be so close to 0 that you can practically say it goes to 0. You can write it off and say it goes to 0. And the only thing that goes to 0 is this r to the n. You still have this 1 minus 0, which is just going to be 1. So all that's left is your term here. A sub 1 over 1 minus r. This is a fixed number. Remember, a sub 1 is not changing and neither is your common ratio. So when you have an infinite series that has a certain type of fraction, you can actually evaluate that to be this. So generally we covered which r's would work and which r's wouldn't work. R's that keep growing are not going to work. R's that shrink will work. However, they can't keep shrinking indefinitely. There has to be a cutoff at 0. Which r's fit that bill? Well, if your r is between 0 and 1, it's going to work. And if your r is between -1 and 0, is going to work. But anything outside of that is not going to work and is going to give you an infinite series that diverges. So we want to make sure that on both sides of your 0, so from -1 to 1, our r stays directly in there. We can't go past these cutoffs here. We can't go past -1. We can't go past 1. We have to stay in between. If we do that, our r is going to force our series to converge. So pretty much if your absolute value is going to be less than 1. So I'm going to put that right up here. If we know this, our absolute value of r is going to be less than 1, then we can determine at a glance which series is going to give us something that we can evaluate and which one is not. We can tell which one converges and which one diverges. So looking at our r, what is going to be our r for these two infinite series? Well, r here is going to be 1/3. How about this one? Well, this is going to say we have r of -4. So if you were to take the absolute value of these, that's going to give you 1/3, and that's going to give you 4. Is 1/3 less than 1? Yes. Is 4 less than 1? No. So that lets you know that this is going to converge while this one diverges. Therefore, you can't evaluate this one. However, you can evaluate this one. So let's do that. Let's evaluate this series and see what we get. So we know it converges, so we don't need this. We know our r, and the only other thing that we need is our a sub 1, which we said to be 1. So if we plug that in to our a sub 1 over 1 minus r, remember that's the only thing you need because this r to the n is going to go to 0, and you're just going to have 1 minus 0, which is just 1. So this is the only thing you need to evaluate. And by plugging this in, you have 1 over 1 minus 1/3, which gives you 1 over 2/3, which is going to give you 3 over 2. Our answer is going to be 3 over 2. So once again, you have some series that you can evaluate, but not all of them. Ask yourself that important question. Does it converge? Does it diverge? You can tell by looking at its common ratio. If the absolute value of the common ratio is less than 1, then you're good. You're converging. You can use your formula, but you don't need all of it. You just need that part right there. However, if it diverges, don't waste your time. There is nothing you can do for that one. It's not going to have a sum that you can find. Let's say we were given a question like this in which we're asked to find our missing n. They gave us our initial term, they gave us a common ratio, and they even gave us our partial sum evaluated at some unknown n. We just don't know which n caused this to have that sum. How do we go about solving for our n here? Remember, this is a partial sum notation, not the nth term of our series. This is the partial sum. So what formula do we have that helps us solve for or evaluate or find your partial sum? Well, that's going to be the formula we've been using. A sub 1 over 1 minus r times 1 minus r to the nth power. This helps us identify what we're going to be using to evaluate our series. This is a partial sum evaluated at n. This is going to be the formula for evaluating your series at n. So we plug in what we know and solve for the rest. So we know our S sub n to be 5,461. We know our A sub 1 to be 1. We know our R to be 4. We know this R to also be 4, but we don't know what our n is going to be. In order to get a little bit more space, I'm going to rewrite this, shrink it a little bit, and then do some simplification. Once you get to this step, you're going to have to whip out your calculator because we're going to have to take advantage of what we know about logs in order to solve for our n here. When we have this, we can log both sides and we'll get the following. We have log of 16,384 equals our log of 4 to the nth power. And we know that we can take advantage of a special property with logs to get the following. Log of 16,384 equals n times the log of 4. Divide both sides by log of 4, which means that our n is going to equal 7. Well, I hope you were able to follow along with today's video and hope you now feel confident in using your formula to evaluate your geometric series. However, if you have any questions about what we saw today, or even your own homework, you can always put in the comment box below, or visit me on my Facebook page at Tutor Me Sempai and tell me all about it there. If you hadn't done so already, remember to leave that like. It surely helps the channel by letting YouTube know that you found a video helpful. And if you found the video helpful, so can someone else. So leave a like, hit the notification bell, smash the subscribe button, and share this video with a friend. Well, that's all the time I have for today. I'm really hoping this helps your homework, and I'm looking forward to seeing you again next week. I'm Courtney. Here's your playlist, and this has been another session of Tutor Me Sempai.